All right, welcome back to the Ethereum Protocol Fellowship Study Group. We are here on week 9, only a couple weeks left. And today we are here with Paritosh from EF DevOps, who is going to be talking about some testnets and prototyping and all sorts of fun stuff. So I'll go ahead and let Mario introduce Pari a little bit more deeper here, and we'll get started. Thanks for being here, Pari.
Hey, Perry, thank you
for having me.
Yeah, it's amazing to have Curtosis here because we already had a presentation by Mario Vega on week 4, a month ago. We've been talking about testing, and I mentioned that he's important in testing the merge and so on, but the merge also would not happen without Pari and EF DevOps, or as they became during the merge, actually, the Panda Ops team, working on testing tooling, on prototyping tooling, on these DevOps tools, which not just enable testing itself, but making it easier for developers to run local or public testnets, shadow forks, and they develop some tools which can help you to monitor even your own nodes and network instances. So lots of interesting stuff. The Panda Ops became a powerhouse of these things, and Pari is kind of the face of breaking the testnets and creating new ones in Ethereum. So it's really great to have you here. I think we can get into it. Get the presentation ready. So the stage is yours. Yeah, thanks again, Pari.
Perfect. Thank you guys for having me again. So today I'm going to be talking about testing and prototyping Ethereum upgrades, which might be an interesting topic for a lot of you because I'm assuming through the protocol studies, once you're done with this, you would want to try out making changes to Ethereum. And the nicest part is because everything is open source, you can run it yourself. And it might just be, there's quite a bit of a learning curve in running a fresh network where you're not ruining anything or you're not breaking someone's system. So we've been trying to make that easier. We've been trying to make the concept of prototyping easier. And through that, we've also built a lot of new testing tools. So I'm going to introduce a couple of those concepts to you today. So the first thing I want to just set the stage, right? Ethereum has something like 20 plus client combinations. There's more every week, every month. We're recently going to start onboarding the Lambda class Elixir client. We worked on onboarding the Grandine client over the last month. So it feels like the number of combinations and this matrix keeps increasing because we try to test each and every EL with each and every CL. So even having like one new client adds 10 new systems for 10 new columns in the matrix for us. Debugging them also gets really difficult, as you can imagine. You kind of have to get a bit into each and every, you have to get in the intricacy of each and every EL and CL. And we had to figure out how to reliably test all of these things. It didn't help if one person ran a script on one machine and then just says, trust me, it works. Up until the merge, I think we mostly just did single client testing. So you would test get in itself, you would test Nethermind in itself, and maybe there were one or two test suites where you would test get and Nethermind together, but not that many. So over the last year, 2 years, we've been focusing a lot on getting this interop level testing. So you have all of these clients spinning up and ensuring that they're all working equally well, irrespective if they're a majority client or not. And another thing is that every upgrade is going to inherit some of this complexity. So we're trying to build something such as that is a bit expandable. So if you build it once, you can use it for the next few upgrades. We don't want to re-envision the testing stack for each and every upgrade. That just adds a lot of toil, adds a lot of time. So we're trying to keep things as generic as possible. And with anyone who's worked with software in the past, that can be very hard because we don't even know what's coming on Ethereum. So how are you generalizing something without knowing it, right? And I'll go a bit into how we've attempted to tackle the problem at least. And competences for ELs and CLs are quite separate. So different teams build different clients. There's not that many people who have an overlap of the entire stack. So we try to separate testing in such a way that it's also conducive to it. So we first try to figure out, is this a CL issue? Is this an EL issue? Then we try to escalate in those directions. So it's kind of pointless if you escalate every CL bug to all the EL devs. That's just how you get people ignoring bugs. So the next kind of step of the introduction is a really big part of our testing stack. They're called DevNets. So you might have interacted with Testnets in the past. The major difference is that DevNets are really short-lived, about maybe even a few months, and then they're down. There's absolutely no long-term support for DevNets, and they might even be local. They might just last like half an hour. Testnets, on the other hand, are more public. We have a reliable testnet schedule right now. So you can expect testnets like Gurley, not Gurley, but Holsky and Sepolia to last for a certain number of years. You can expect the network to be up. So the DevNets themselves are a testing mirror of the Ethereum base layer. So they have the same components that Ethereum mainnet has. They contain execution clients, they contain consensus layer, beacon node clients, they contain validators, you have MEV infrastructure on there. And the way we do it is, because we control the entire DevNet ecosystem, we can set it up in whatever configuration that we want. So you could imagine that for whatever reason, we want to test a super majority bug, right? So we can set up that a majority of client validators are running a specific client, and we can simulate that incident. So having this level of control on DevNets allows us to deploy forks and changes without affecting mainnet, without affecting any stable testing network or anything, while they are still public. So community members, so you guys, for example, are more than welcome to come test with us. An example, right now we don't have any Petra DevNet up. We're planning on having one up over the next few weeks. But we do have Verkle DevNets up, for example. So you could take part in a Verkle DevNet, try and break it. And if you break it, then it's going to make its way into a fix, and you have your fame there. Yeah, and like I mentioned before, you're able to design all of these edge cases, these network faults and things like that, that are kind of harder to do anywhere else. And testing today, so we actively are talking about a Petra DevNet, TBD. Maybe in the next week, 2 weeks, you will be seeing something. A lot of our focus right now is on Verkle, so trying to get some Verkle transition tests going, making sure the tooling is ready for the next fork, because we have some amount of downtime to work on it right now. We recently relaunched the Costinen DevNet with some changes that were found from earlier iterations. We're also doing some prototyping. So inclusion lists is one strong example. Another one is EIP 7441, which is WISC, where you have some amount of base layer validator privacy. So we also have some long running testnets that achieve that. It's also not just DevNets that achieve that, and it's not just future forks that DevNets can use. Sometimes current networks also current clients also need some sort of testing, right? For example, Ethereum JS wanted to have SnapSync support on their client, and doing this on a full-fledged testnet is quite heavy. You have a lot of blocks, it's a lot of state. You might not want to target that immediately. So we set up a small scale Ethereum JS SnapSync DevNet that they can just use for that use case. And we often do run, we call them big boy beacon chain tests. So they are maxing out any one parameter of the beacon chain that we think makes sense to max out. So an example might be increasing the validators to 1.5 million validators or 2 million validators. And this is indeed a test that we ran before committing to how big the validator set on Holsky will be, so that we know that the clients are actually able to handle such a big network. Same with blobs. We would spam blobs and see, hey, if in our controlled environment we're not able to do X amount of blobs, there's no way that we'd be able to do this on mainnet. So this sort of DevNet level testing allows us to achieve a lot of different things there. But DevNets require a lot of coordination. You would want a bunch of client teams. You would probably expect a DevOps team to be setting up this network, and it takes some amount of effort to coordinate everyone. And we don't want to always do that, especially if we put in all of that effort and the network breaks just because a client didn't start up or just because someone had the wrong specification implemented. It's a lot of toil for too little effort. And at some point last year, we realized this, and we wanted to do a heavy push for local testing, because then I can spin up a really small network to sanity check that everything is working before I commit to the bigger DevNet. So this also allows us for faster iterations. So I can have, 10 different parameter changes running over 20 different DevNets, all running on one laptop, and then figure out, I found this bug in this one, and that one, and let's see which is the optimum that I'll commit to for a DevNet. It also allows us to work async on a lot of features. So if client A and B say they are feature complete, we normally publish like a config that everyone can use, and then you can update and append your own client and see if interop works. And if it works, then you already know that when the DevNet happens, the DevNet will also work. And to also help this local, fast, iterative testing, we also allow you to configure slot times. You can change the fork epoch version. You can do the entire MEV workflow. So there's a lot of really nice things that can happen here. And I'm going to go through a couple of examples of how these local testings look. And I do definitely want to focus on this for a bit, especially in the context of prototyping, because I think this is a really, really powerful tool for not only understanding how Ethereum works, but to know what components Ethereum has, and for whenever you feel ready, how to test your own changes on sort of your own network, that you get some more confidence of it. And this setup that we have, it's also very scalable, and we've kind of achieved this via this tool that's called Curtosis. So Curtosis is, you can imagine it as a CLI tool. It consumes YAML, and then it parses this YAML via the definitions, and the definitions are all in Starlark, which is a Python-based language. And what it spits out is something that Docker as well as the Kubernetes engine can understand. So you're going from a YAML definition into a Ethereum network that is deployed either on your local Docker machine or on a remote Kubernetes instance. The reason we want to support both of these is for a local Docker instance, it's great if you just want 2-3 nodes, you just want to set up something quick, you want to see if a fork works in under 5 minutes, and then you're done. Whereas if we want to do bigger tests, say you want 500 nodes because you want to test some edge case, or you want to make use of the Kubernetes layer abstractions that are offered to you, for example, chaos testing, right? Then you want to support the Kubernetes engine as well. So we kind of offer, or you want to have a more production system where it can run in the cloud, someone can access data from it, you can have like a public DevNet in the cloud. You can use that Kubernetes engine for it. It's all configurable. You can have a look at the Curtosis documentation, and there is a repository. I highly recommend that you guys are also going to this repository, and please, over the course of this call, try and download Curtosis as well as make sure that Docker is on your local machine, because towards the end, if you want and try to run some of these examples and you have questions, we can also talk about the questions. It's extremely simple to run, and I'm just going to go through this definition once because we're going to be using this definition also later on. So Curtosis, name of the CLI you're using, you want to run something. An enclave is sort of a namespace. It contains what this network will be called, and other networks won't touch this. So it's just some amount of separation. You can have more than one enclave on your machine. You can do a lot of fun things with with enclaves. We normally just call it Ethereum network or ETH2 or whatever you want to call it. The next GitHub link that is pasted there is the Starlark definition of what the network needs to look like. This is just generic understanding. This definition, for example, defines what a get node is. It defines what the YAML fields mean. What do I do with Genesis time? It defines all of those things. It's very extendable. And the really cool part is if you clone this Git repository and you make a change to the Starlark, you don't even need to push it. You can just replace that remote GitHub URL with dot or whatever the path, your local path of the repository, and Curtosis will pick it up. And Curtosis won't then deploy a network as defined in GitHub. It'll deploy the network as defined in your local machine. So not only can you modify parameters of a network, you can also modify what it means to be a network in itself. The next one is args file, and then you pass a file which has a bunch of predefined parameters. And I'm going to go through a couple of them to show you what type of networks you can set up with this local testing tool. So here's an example of a YAML definition. So you define the participants. You're saying you want one participant that is a get teku node. So this will be get EL, teku, CL, as well as validator. And then you want one participant that is a Nethermind EL and a Prism CL as well as validator. You can also override every single part of this, by the way, and I will talk about overrides later on, but every single bit of Curtosis is overridable here. And then you are defining here that you want some additional services. You want this network to have a transaction spammer so that there's some transaction load on the network. You want this network to have a blob spammer, some blob load on this network. Dora is an explorer, so it'll give you a URL. You can access a local explorer that will help you understand what's going on in your network. You'll be collecting all the metrics and pushing it to your own Prometheus instance. And a snooper sits between all the APIs that are available. So between your engine, in your engine API, in your beacon API, and every one of them, and it just spits out every single thing that's happening on that interface. So it's a man in the middle. And it's very useful for if you're doing a new fork and you actually want to know, hey, the CL sent something and that broke the EL. Can I maybe figure out what message the EL sent me so I can reproduce this bug? Saves us a bunch of time having this sort of man in the middle. And Key Manager enabled enables the Key Manager API, and you can do whatever you want with the Key Manager API as well. And I'm guessing a lot of you are in the MEV environment, or at least curious about the MEV environment. And we also support the entire MEV workflow on Curtosis. So if you do, for example, mev type full, then it will spin up a local relay. It'll spin up a local database for your for accessing all the relay validator registrations. It'll spin up mev boost so that your validator can connect to the relay. It'll spin up a builder. It'll use all open source images. So most of them are from Flashbots, and you can override any of them in case you're building your own relay, in case you're building your own mev boost implementation or whatever it is. And one important thing to note here, if you notice in the previous list, there was a participants, whereas here there's no participants. So whenever you don't specify something in Curtosis, it just uses the default. And the default is, I think, one participant with the Geth and Lighthouse. So that's what will be spun up in this network. And here we're also having a few additional services. So there's custom flood that comes up. And what custom flood does is it sends very mevable transactions so that there's some juicy payloads that the builder can build. Otherwise, the builder is not building anything that the validator is going to propose with. And what I meant by overridable, if you look at the MEV params, so I'm launching with custom flood that's also available earlier, and I'm specifying the mev relay image. And what this means is you no longer want the default mev relay image that Curtosis ships with, but instead you have your own mev boost relay that you've implemented, and you want to use your Docker image there. So that's also possible. And this is extremely useful for us in rapid fork testing. So we can have the latest version that has not been released yet, override it here. And it's only, if it breaks something, it'll only break something in my local testing environment, nowhere else. And to make things faster, you can also override certain parameters. So anything that makes sense to override in the consensus specs, there's a file called config.yaml. So this is the definition of what a beacon chain looks like. Anything there that makes sense to override, we allow you to override here. So one of them is seconds per slot. So Ethereum beacon chain today has 12 seconds per slot. And here I'm saying that's too long. I don't actually care about waiting for 12 seconds. I don't actually care about finality. I just want to make sure that my payload is getting delivered. So you're overriding it to once every 3 seconds. And now you have 4 times the number of calls happening, which means the chances of whatever you're testing to be triggered are probably 4 times as likely. So yeah, so the next thing is I've shown you guys how you do some local testing. The question is now, how do I actually prototype things, right? So like I've mentioned earlier, Curtosis works on the concept of everything can be overwritten outside of the network basics. So a simple example is in the mainnet spec, there will always be 32 slots per epoch. You can try to override it. It's not supported by any client. So you can specify it in Curtosis if you want. We're just going to ignore it because it's a sane check that we know will break the network. Like that, we have a lot of sanity checks that make sure you can't break your setup too much. So as long as you read the docs, as long as you change something that we specify over in the docs, chances are it'll work quite well. In case you want to test protocol changes, you might want to update or override the client images itself. So you don't want to use Nethermind latest. You might want to use Nethermind fork that you have built yourself. In order to test new tools, you can run an existing Curtosis network. You can run like a tiny Curtosis network. And once at the end of the Curtosis run, it'll give you all the API endpoints. And your tool can connect to those APIs, and you can test building whatever you want to build. An example is we've built a local explorer with this. So we no longer have to sync a whole network. You don't have to do all of that. You can just sync a local network, which is a lot faster. And then you can make sure that your Explorer works as expected before you do anything wild. A lot of people also do this for smaller tools that they're building. So there's this one tool where you can have a CLI that kind of notifies you when your validator is selected for proposals. It's being built by someone who works at T-Mobile, as far as Telecom, as far as I know. And he's using Curtosis to run it locally to connect to a local DevNet. So he controls the entire validator set, and he wants his tool to do a lot of other things, and he has entire control without relying on a public network, without spending gigabytes to download something, keep it in sync, etc. And in case you want to test quicker forks, like I showed earlier, you can change the second per slot. You can change when the fork happens. So you can say, hey, why don't I have my fork happen at epoch 1 already? So if I do epoch 1 as well as set the seconds per slot to 3 seconds, then pretty much in about 2 minutes, you're testing a fork, which is extremely fast when you want to iterate stuff, when you want to prototype things. And here's an example of prototype testing. So Verkle is a huge beast and it's a big fork. And we've been trying to support it with local testing as much as we can. So here's an example of how we can test the transition, the Verkle transition locally. So if you copy this and you run it in Curtosis, you're basically testing a Verkle transition. So I'm going to go through this from top to bottom. So what happens is right now I'm specifying a participant list, and I'm saying I want a get node, and I want the get node to run this particular Docker image. This particular Docker image is built from a fork of get by Guillaume, who's working on Verkle, and he's doing a transition post a network genesis. And there's a Lodestar image that G11 Tech has built that supports the Verkle transition, because both the EL as well as the CL need to have a concept of what the fork is for this to work. And I want 3 of them. And you can specify count as whatever you want, and it'll replicate the same definition for all the participants. And then in my network parameters, I'm specifying that at the time it was called an Electra fork epoch. We're still rebasing, so don't pay attention to that particular name. But it is Electra fork epoch 1. So the transition will happen at epoch 1. The network will start roughly 100 seconds after I run my Curtosis command. And you might want to do this for a certain number of reasons. Maybe there's an amount of time that takes for you to spin up all your terminal windows with the logs. Maybe you want to wait some time for some processing that your node has to do it init. Maybe you just don't want to have it immediately so you don't miss anything. So in this case, we're just doing it with Genesis delay of 100 seconds. And then Snooper is enabled, so I'll be able to see each and every single call that happens between the EL and CL. And this was very useful early on because the CL dev could say, oh, this is how I interpreted the spec. I wanted to have these calls. And the EL dev is like, yeah, but that puts me in this state. Maybe you send it this way instead. So it helps us to actually see what's going on. Persistence true is important in case you want to have this network running for a longer amount of time. It just means if a container restarts or whatever, it starts back up with the same state. So if you have persistent true, you could say Curtosis stop participant number 2. You can wait 10 seconds or whatever, 2 minutes until some blocks are built, and then you can start that particular instance again, and then that instance will start syncing to the head of the chain. So you're also testing sync in a way. So you can use this for a lot of really cool things. Or it could also be something as simple as, hey, if I built a client and I shut down the node and I started back up, will it even start back up? That is also something you want to test, right? And I'm wanting to launch some additional services. One of them is Dora, the Explorer, and the other one is Asserter. I won't talk about Asserter now. I don't want to overload you guys with tools, but yeah, for now, kind of get this is how you would do prototype testing. So if you have your own EL, your own CL fork, and you want to test it, all you have to do is replace EL image and CL image. And maybe a good first example is fork any one client, doesn't matter which one, whatever language you're comfortable in, and just add some log message saying you were here. Build a Docker image, put the Docker image here, and then once you start the network, in the log, it'll say you were here. It's a nice first start to understand how the prototype testing system will work. So once people are kind of comfortable with local testing, what we normally do is upgrade to remote testing. And I've mentioned the reasons earlier. Remote testing needs a lot more synchronous time. We try to do it only once we feel like clients are ready. Verkle, for example, has a lot of local testing for a rebase that's going on, but we've deployed some older versions for public DevNet testing. Even though they do take some amount of effort and time, we want to make them as easy as possible to set up when we're doing it. And they used to be very error prone and time consuming because the definition of how to spin up a DevNet, what parameters are there, I think 2-3 years ago, every single team was maintaining their own start testnet scripts. Earlier, at least, that's largely how that worked, and I'm sure they still do, and it's very good that they do. But it gets hard to do interop testing if you're reliant on those scripts. That it's harder to modify things. And it becomes very easy for a drift to occur between setup configs and customizations you might need. So Verkle needs quite a few customizations on quite a few levels. So we have Verkle has a specific type of genesis, and that genesis requires you to use a fork of another library that is using a fork of another library. So there's like 3 levels of forks that are required and needed to be maintained for it. And now you can imagine if we're doing this across many clients, it just starts to get very tedious. There's a huge drift. I might not want to. You'll drift so much that you might not be able to merge stuff back into your main whenever you're ready. Right? So what we did was we split the bare bones logic of what is a node and what needs to happen on a network, i.e. generate validator keys, get genesis, start a node, wait for a node to start up, get the node's peer-to-peer address, shut down a node, clean up a node. We've taken these generic definitions and we've used we normally write all of these things in Ansible. Ansible is I'm going to call it a fancy scripting language. It's not a language really. It's like a fancy scripting methodology to do things across a lot of nodes, a lot of cloud instances, right? And there's a concept of a role. So a role is sort of like a function that you can call, pass some parameters, and what you passed in is what happens. So we've generalized these concepts into this Ansible collection general. And then we've moved generic components into their own tools. So Genesis is a concept that almost every single DevNet has to do at some point, right? If you don't have Genesis, if you don't have the Genesis files, the network will not be able to start up. So we built this Genesis generator tool. All it is a Docker file that wraps through a lot of tools and scripts. So there's some sanity checks, some logic, some methodology on how you call it, but it's very configurable. You're able to handle the case of Verkle that I just gave you, where there's fork over fork canonicalized there, as well as mainnet Ethereum, as well as shadow forks, as well as the next Spectra DevNet, all within this one repository. And the interface between this repository and the Ansible connection is defined. So they're tightly coupled in that way, but you can modify both if you want, and you can get a whole new different thing. And the next problem was tooling. If, for example, I have Verkle, the Verkle DevNet changes so many things that my Explorer might not work out of the box. I might need forks of my Explorer. It gets hard to maintain that, and it gets hard to keep them up when a network is running. It gets hard to scale them up. You have operational issues there. So what we do is we use Kubernetes, and there's a concept called GitOps. So GitOps is basically what is on Git is what gets deployed on your Kubernetes instance. It's one-to-one. So you define what you want on GitHub, and Kubernetes makes, or this GitOps thing, we use Argo, it makes it happen for you. And these definitions happen via another packaging language, packaging system called Helm charts. So this will, for example, spin up all of our tooling for us. So we now have a way to spin up Ethereum nodes. We have a way to spin up what a network is, and we have a way to spin up what the tools are. The question is, how do you bring all of these disparaging things together, right? So what we've done is we've generalized the setup for all testnets possible into this repository called template testnet. So what template testnet does is it has template testnet has Terraform code to spin up the network. It then uses the Ansible code as you define it to spin up the nodes, as well as to spin up Genesis information and get all of that and put it somewhere. And then it also spins up the entire definition for what your tooling needs to look like. And then once you push this entire thing to GitHub, GitOps just makes that tooling magically appear. So GitOps also makes sure that your certificates appear, that your URLs look nice, that you have a load balancer in front. All of those nice things are just taken care of. So by splitting these things up into small components and then combining them together in template testnet, when I have a huge diff, I can maintain it nicely in template testnet and move stuff back into the template as and when it becomes important to move it back. So you're reducing the amount of drift that happens between template that setup configs. We've successfully been using this for about a year now. We did the entire Denkun fork at the same time, testing Whisk at the same time, testing Verkle at the same time, doing other testnets, and we reuse this exact same infrastructure for our Holsky nodes, Sepolia nodes, all of them. So I would say it's a relatively battle-tested system, and we're quite happy with it. It's not to say it doesn't have its downsides, but I would say we've minimized the downsides as much as possible once someone understands the system. I'm not sure how we do questions, but maybe this is a good spot to stop for questions. Maybe Mario or Josh can tell me if that's a good idea.
Yeah, great. Thank you so much, Pari. We have discussion going on in Discord here. People are asking questions. I'm sometimes answering if I'm able to answer. So we've been going through it. People are running Curtosis here. And let's see if you folks have any questions regarding the Curtosis. If you ran into some issues or something, let us know. I've also updated my local Curtosis binary and ran it again. After a while, I have to say it works super nicely. The quick start is very easy compared to like scrambling together bash script from like some client team to run a testnet 2-3 years ago. Like it's incredible. Yeah. There was a question, how are the Docker images published? I shared them, the Eat PandaOps on Docker Hub. Maybe if you can tell us more about that, like how do you publish the images for testing, and maybe whether you use also images from the client teams themselves.
Yeah. So we do it two ways. The first one is, maybe I can explain the problem to begin with. Before we started, every client team published Docker images, and they still do. But when or what triggers that Docker image publish varies wildly per client. So some client teams publish on latest, some client teams publish just the master main branch, some publish on each and every PR, some publish forks, some don't publish forks. It was a bit of a headache to always ping the dev working on the fork, who then had to reach out to their DevOps person to build a Docker image for us. It gets very out of hand to do this. So what we did is we Of course, when there's a client image, we use the client image because I think that's a better way of testing. But when there isn't one, for an early fork, for example, that is based off of a lot of other forks, we have a generalized Docker image builder. I've shared the link in the private chat here. Maybe Mario or Josh can move it over to the other chat. So this repository is able to build the client images of each and every single EL and CL out there. There's a config.yaml file, and that config.yaml file is consumed by a scheduled builder. So once every 2 hours, for a branch that we think is interesting to target, we build and preemptively publish images. So every image we publish will have a generalized name, so latest, devel, whatever, that gets updated every 2 hours, as well as latest dash a SHA commit slug, so that when we do testing, I don't want to run latest and say, hey, my latest is broken, because that means nothing to a developer. They want to know which commit you ran when you ran it. So you can choose. In some cases, for example, CI tests, it makes sense to just use latest. In some cases, when you're doing a local test, it makes sense to specify exactly which commit hash you're doing. So you're able to build every single EL and CL. And if you go to the Actions tab over here, we also support manually building them. You would need to be invited to this repository to build, because it gets very easy to spam the builder with requests otherwise. But almost any client dev who wants access gets access. There's no real gating over there. And also, if any of you really feels like you are actively testing something and you want access to this builder, please let us know. And then if you choose, for example, you want to build the Ethereum JS Docker image, and on the top right, there would be a run workflow. And with that, I can specify which repository to target and which branch and what the resultant Docker image should be called. And with that, I can do this ad hoc testing of, hey, I don't want to push this fix into the Ethereum JS main repository. I have this tiny fork of mine that no one else knows about. Can you use this? I can still build a Docker image from there without relying on my local machine. And it'll build ARM images, it'll build Linux x86 images, it'll build you a Mac OS image, all the nice stuff. And then everyone's just happy. You can just target it always results in an ETH Panda ops / client name Docker image. Yeah, I hope that answered the question about the Docker image. That's usually where we build them. That's usually how we consume them.
Yeah, it totally did. I'm just sharing my screen, showing the actual repo. If the link gets lost in the dismissing through the presentation, just wanted to show that. Awesome. Yeah, thank you so much, Barry. Thank you for answering that. And if there are any issues, questions, or Curtosis, you can still keep asking.
Yes.
Maybe we can ask one more questions before we move forward. Can I point the Curtosis to the local get, or is it only forks of remote repos or Docker images?
So you can also point Curtosis to local anything. So if you don't want to use, if you use GitHub / whatever, then it's remote. If you just point it to / and then put a relative path, then it just uses local.
Yeah, that's what you said. You can just pull the repo, you can just clone the repo and do your modifications right locally. Yeah, it's very, very nice that you can just provide a local path.
Exactly.
Yeah. Awesome.
Yeah. And the whole Curtosis setup is completely open source. You can mess with Curtosis itself. You can mess with testnet definitions. You can mess with basically anything you want to mess. The whole stack is open sourced.
Okay, awesome. Yeah, thank you, Barry. I think we can go on with the presentation, and we'll get back to the questions.
Perfect. So the next one's a bit of a loaded topic, shadow forks. So you might have heard of shadow forks both in the context of the merge as well as almost single Ethereum upgrade that happens. So shadow forks allows us to, what it essentially does is you take a main network and then you fork it. but you fork it just in a small subset of nodes, leaving the main network untouched. As a result, you inherit the state of the main network, but if you configure a fork, then you're forking in your tiny shadow chain. There's a nice visual in the next graph, but before we get there, doing this setup helps us understand and check compatibility across clients through the entire lifecycle. So you are inherently building a mainnet block. It's just that Ethereum mainnet, for example, rejects your block because it's non-canonical. But you've gone through the process of building a mainnet block, which is the important part from a testing perspective. This allows us to check a lot of assumptions. So for example, when we were doing blob testing, if for whatever reason building a blob and verifying that with a mainnet state size was infeasible, we would have seen that here. This was extremely valuable in the merge because we would set an override TTD that just happened a few blocks in the future. And when we do that, you're essentially simulating the merge without touching mainnet Ethereum, which was very powerful to have as a testing tool. You're stress testing the client. This will be as close to mainnet as possible, or as close to whatever network you're shadow forking as possible. So it comes with all of those assumptions. Because of the way peer-to-peer works, you still stay peered to the main network for a significant amount of time. So you're still importing transaction load. So if mainnet Ethereum has 100-something transactions that are happening in a block, your shadow fork also has those transactions included. Not all of them probably, but there are some intricacies as to why they won't get included the same way. But fundamentally, they are included, which is really, really useful for stress testing how a network performs. And you're controlling the entire validator set, so you can take care of how the network needs to be. And it acts as a release test. So this is kind of the last stage of the testing DevNet testnet cycle that we see. If you're passing on shadow forks, it gives us quite a lot of confidence that when we do the same upgrade on mainnet, it's going to work as expected. So I'm going to preface this with simple in principle. It is simple, but it is a bit of a hard-ish concept to grok in the beginning. So what you do is also ignore that it's using Gurley. I haven't updated my slides. It should be Polsky or Sepolia by now, but or ephemery. But for now, let's talk about Gurley. You take the Gurley Genesis file. You can find this in github/eth-clients. There's a repository there for each testnet where all the Genesis files exist. I modify the Genesis file. So forget this is genesis.json. And I add a fork timestamp. So I say Petra timestamp : 1 hour from now. Now I set up a new beacon chain with validators, which also has the Electra fork configured at the same exact timestamp. And the deposit contract points to the earlier Gurley chain, right? So now what you've done is you have a subset of validators in a new beacon chain that understand when the fork is happening. You have a subset of execution nodes with your modified Genesis JSON file that think a fork is supposed to happen at some time. No other Gurley node in the network has this configuration, just your subset. So when this timestamp is hit, so in this case, when TTD was hit, the canonical chain, the Gurley chain that you or me or anyone else is using, just continues as if nothing happened. But my local nodes with this modified Gurley config will think a fork has happened. So they will execute the fork code. And since the EL just builds the block when the CL tells it to, and the CL is configured to build a block with this fork timestamp, it will build on top of the last canonical Gurley block. But this new Gurley block is invalid in the main chain because it was built by a validator that no one in the main chain knows or recognizes. But in my controlled validator set, all of them know and recognize that validator, so they accept it. So what I've essentially done is forked the EL to build on top of the girly state, but just for my subset of validators. No one else has any indication of this. This new chain builds on top until infinity. Everyone who has a balance on girly will also have a balance on this shadow fork. Some intricacies, of course, but all of it is essentially the same. You're building on top of an existing network. There's some spearing complexities on top. There's some mempool complexities on top. I won't really go into that over here, but you would stay paired. You would still fetch from the mempool for a certain amount of time. Slowly, the state will continue to diverge because you're allocating transactions in different orders. Your balances go out of sync after a while, and then you stop peering with the main network, and then your shadow fork is just its own thing and will continue until you shut it down. But for that period of time where it stays connected to the main network, it's very, very valuable. And based on most testing, this period of time is not trivial. It stays like 2 days, 3 days, depending on the size of your network and number of transactions and what you do with this shadow fork and so on. I know it was quick after the previous question session, but usually shadow forks, since it's a biggish topic, I do want to stop for questions before we talk about what tools we have and what you can play around with in the testing world.
Right, thank you, Perry. Yeah, so shadow forks are very exciting. I love to follow them and see what nodes drop off, and it just gives us this exciting feeling about getting to the TTD to the timestamp to fork something. It's always like um, a little moon launch or something like that. I'm waiting for some questions to come in.
Maybe while we're
Forks.
waiting, there's a
Yeah.
link I've sent, and you could open this link, and then I can showcase what is happening in. So you can actually, we've added shadow forks to Curtosis. So you can do like a one-line shadow fork just with the Curtosis command. And we do this with Verkle on a CI on a nightly basis. So I talk about this later as well, and I think I've linked it later in the slide, but maybe since we're up here, Mario can open the link and we see. Yeah. So
Yeah.
what you see here is the Curtosis config. This was updated just 3 hours ago. This is a live testing system, right? So Guillaume is working on rebasing the Verkle code base such that both the transition as well as Verkle Genesis happens in the same thing, and it has the concept of Deneb. So this is the rebase that we are testing. We've defined one-time loadstar get and one-time, this time it's both loadstar get. You could also just change count 2 and achieve the same thing. I want Electra to happen at fork epoch 1. So this is when the Verkle transition actually happens. And here I'm doing network Holsky shadow fork Verkle and network sync base URL. And this, we're running it locally. So we have an S3 bucket with the Holsky snapshot. So what this does is Curtosis will go to this IP address and fetch the S3 bucket that has the entire Holsky state. It will then start get with this Holsky state, and it will have a Verkle fork that happens at epoch 1. So the only part missing in this situation was how do I know the transition succeeded or not, right? And just for some more sprinkling of clarity, we do this on a Kubernetes cluster. So if you see global node selector, that doesn't mean anything to anyone else except our Kubernetes instance. It will run this transition on one machine that knows how to access that IP address. So we're running this other tool called Asserter, and you might have seen this once or twice, and in the future I will be going a bit deeper into what it does. But what Asserter does is it checks and asserts that a certain condition is true or false. And in this case, Asserter is fetching this test definition, Verkle conversion check, and every epoch or so, it checks if the Verkle transition was a success. So from the CI perspective, what this looks like is once a day, I'm pulling the latest image from Guillaume's fork. I'm fetching the latest Holsky snapshot, I'm going through the entire worker transition, and then Asserter will give me a tick or a cross in GitHub CI that tells me if the transition was a success last night or not. You can also trigger this manually. So if I've made a big change and before I merge in a PR, I want to make sure that it's working, I can do this. And this is just an example of Workl, right? There's no reason that this cannot happen otherwise. So you can also run this locally on your machine. If you don't specify a network sync base URL, you're just going to sync a Holsky node locally. Not a big deal. It'll just take more time. So you probably want to add a bigger Genesis delay. But 100 seconds is enough for a local network to pull a snapshot. So we're running it with that.
Awesome. Thank you very much, Pari, for showing us this. Because that was the question there, like what is the tooling to run Shadowforks? So you just went ahead and did it.
Yeah. So there's one example there, and maybe there's another quick example. One sec. It should be in. Yes. So I will send you another link. 1 second. So there's another link. If you could open this, Mario.
Yes, I can. Good.
Yeah. So this is our CI runner for Curtosis itself. And we want to test that we're not breaking any functionality. So we've just defined a wide range of things that you can do with Curtosis, and then the CI just runs it on before a PR. So if you ever need examples for how to configure a certain thing, this is the place to look. And for example, you can see Hosky, Shadowfork, Workl, no run, bit up in the H. Yeah, that. So here you're looking at, maybe go back and look at the next example. So without Workl. Yes. So this example is where you are simply doing a Hosky shadow fork that will run the latest version of Geth Teku. That's it. There's no complexity. And you have to, of course, set Denkun fork epoch as 0 because the Hosky network has already had Denkun. And then this will spin up Explorer for you. That's all this file is doing. So you can play around with shadow forks all you want, single one-liner. You can override the images if you want to test your changes. You can, do a lot of things. And we also support ephemery. Yeah. You can, by the way, also use Curtosis to sync a live network. So if you go back to ephemery, this will spin up all of these participants and configure them to sync to the latest iteration of ephemery. Nothing else is needed. You sync to ephemery, and that's it. You can change ephemery to be mainnet. I really don't recommend mainnet because Curtosis is a local testing tool. It's not meant for mainnet level 1 terabyte node. Your laptop will get filled up. We only do mainnet on Kubernetes, but you can do Holsky, Sepolia, whatever it is, and it will sync that network that you specify. If you do, so the naming convention, we also try to standardize things. So it's always network name dash shadow fork if you want to do dash shadow fork. And then if you put Workl after that, then there's some Genesis magic that happens that uses the Workl Genesis information. Yeah.
Awesome.
Yeah.
Yeah, thanks so much. This is very interesting. Digging into the package repo. So there are some questions on shadow forks.
Sure.
How do we define a successful transition? It's simply clients not failing off, but maybe you have some better definition and some tests that you measure.
Usually for us, the transition success right now is just if all the nodes are at the same head, and if we're working with the Gets guys to add an API to know when the transition is done. And then we yeah, we just wait for them to all be on the same head, and for the logs, I think, to not show that it's the transaction in progress or something. But yeah, we want to make that configurable via API so that you can just query the API and it says transition in progress or transition completed.
Thank you. And a question, whether you can run a new validators and remove validators from shadow forks, whether it's like further testing that you do.
Could you repeat that? If you run new validators?
Yeah, if you after the shadow fork, whether like one of the tests you do or you can do is like doing your deposit, spin up a new validator,
Yes.
withdraw.
So I will talk about that particular question when I'm introducing Asserter to you guys. But for now, the answer is yes, and I will show you how.
Okay, awesome. Thank you so much. Yeah, there were some questions for like demoing the there's the issue with Curtosis, but it's a log, so maybe we can leave it for later. Yeah,
Yeah.
I guess you can.
The Curtosis guys also have a Discord. They have a product support page. Please feel free to put stuff there. Because we actively change stuff, sometimes we also break things, but we try as much as possible not to break.
Okay. Yeah, awesome, Perry. I guess go ahead and we will get with the questions when we start the
Perfect.
presentation.
Yeah, I think we have roughly about half an hour, right, for the rest of the call.
Yes. Yeah.
Perfect. That should be enough for finishing in questions. Okay, so overview about handy tools. We have a website, ethpandaops.io. Please visit the website. Um, Pretty self-explanatory. There's a tools page on the top right. You can see all the tools that we maintain, as well as all the tools um, that we have, along with some blog posts on how to use them, and more are coming. There's an Asserter blog post coming up this week or next week latest. All the code bases for every single tool we build can be found in GitHub. Everything is open source except for our logic is the tool is always open sourced. The config, depending on if there's secrets or anything, might not be open source. But every single tool, every single test we have is open source. From a licensing perspective, we tend to use MIT. Sometimes it may be GPL, AGPL, but 99% of the time is MIT. So feel free to fork away, feel free to make PRs, add features. We're very happy when people add features. Yeah, also happy to modify our tools to support anyone else. The tools get reused by other networks. They get used by L1s, L2s. Some of the DVT guys like Obol also use some of the tools. So we try to accommodate everyone's needs so that there's also better maintenance. That's how you build an ecosystem around things rather than everyone building their own thing in silos. There's some reading for you guys, and I will make sure to also put this later in some doc or copy it around. But there's a testing overview doc. So both Mario and I spent some time over the last week compiling it. It is not exhaustive yet, but we're getting there. It aims to define every single major testing tool that we have, as well as who the maintainer is, what the tool does, and what layer of the stack the tool is. As well as what layer of the stack the tool is touching or testing. So please have a look at this one. As we go into Pectra, we're also going to use this testing overview doc to try and understand what order we should test things to coordinate a bit better between the different teams. If you're interested in testing in itself, find a project, start contributing, keep an eye out on ETH R&D interop. Usually you might notice, oh, this is hard, this is difficult, does anyone know how to do this test? Pick it up, make a tool, make a PR to an existing tool, add support for a new fork. Usually when a new fork is defined, there's like a list of PRs we have to do, some for some libraries, some for some Genesis tools, some for tooling. Help us make those PRs. That's a great way to learn about a new fork. So the first tool, big one that I'm going to talk about was Curtosis. So We've covered it, I think, in quite extensive detail. So I won't be going more into Curtosis. Please have a look at the GitHub test, join the Ethereum the Curtosis Discord chat server in case you have questions. They have a great support team. Yeah, like I said, everything is open source. Feel free to use it as much as you want. Template DevNets. So I did mention this. The template DevNets repository is combining all of these different Ansible, Terraform, as well as Genesis files, and all of this into one coherent repository. So GitHub has this feature where you can fork a repo out of a template, or it's kind of like implement a template, right? So if you go to the template testnet, there should be a button somewhere that says use this template. And what that will do is it'll create a new repository using that template in your namespace. And we often do this. For example, if you go to Verkle DevNets, on the top somewhere it'll say forked from template testnet or part of template testnet thing. So if you ever want to know the entire diff between our template and Verkle, just make a PR between main and main, and you will see all the changes required for Verkle testing. This is very useful if you want to run nodes on a larger scale. If you want to run your own Ethereum nodes, so I run Ethereum nodes at home, we run Ethereum nodes in the office. We use this exact infrastructure for doing all of it. It's very mainnet compatible, it's very safe. Feel free to use it. There's not much magic that happens. This level of testing you normally get to once the local testing tools are inadequate. Tends to happen a bit later in the fork process. So if anyone is questioning it, I would say spend more time on Curtosis, because with template testnet, you need to know what Ansible is, you need to know what Terraform is before you can actually start doing stuff. And if you, for example, spin up a Terraform, a bunch of cloud instances with Terraform, that's also going to cost you money. Whereas in Curtosis, the worst thing that can happen is that you have a Docker container running for one day too long. There's no risk involved there. So play around with template testnet, especially if you're someone who's looking to get into bit more DevOpsy role, bit more deep insight into how DevOps works, then this is the place to go. So now for the big one, Asserter. So you can find the Asserter repository under ETH Panda Ops. The idea of Asserter is it asserts a network level expectation. Example, can a network handle deposits? Can it handle a transaction that has every opcode being called? Can it handle a reorg? That's the question that Asserter tries to answer. And it's a generalized testing tool, so you can use this for assertions on any network. You just have to define what the assertion is, what the health check or what is correct wrong is, and then you have to run Asserter with that test definition. And you have to point it at which nodes to check. So when you do these three things, Asserter will check those nodes based on your definition, and it will assert the assertion that you've given over there. So the example that I was mentioning was the transition of success. So ideally, we'd like to have it in a place where I can just query all the APIs, and the API says transition success equals true, or transition equals complete. And then Asserter will say, okay, the Verkle transition was defined as when this API call returns true, then it's done. And you can add a timeout saying if it doesn't happen within 1 hour, then it's a fail. And Asserter will say, okay, didn't happen within 1 hour, let's return a fail. Asserter can be interacted with via the API, so you can run it and then configure tests. This is very useful in some cases like Kubernetes, or if we have public instances. You can also run it at runtime with all the tests defined. You can fetch information from Asserter via its API. You can fetch information via its logs. It's kind of like this middleware that does everything you need it to do for ensuring a network behaves as it should behave. Because the timeouts are also configurable, we do deposit tests with this, we do withdrawal tests with this, we do slashing tests with this. So I can define how Asserter creates a slashable condition, and then it executes the slashable condition for me, and it makes sure that every node has accepted the slashing. So you know that when and if this happens on a real network, that all of these are working. You can also configure something like make sure that every node in my local DevNet has proposed a block at least once. And this is really useful for fork testing, because you want to make sure that you're not breaking attestations, that you're not breaking proposals, that you're not breaking the fundamental parts of what makes a network. Yeah, so you can do a lot of these things. And we also do, we're currently focusing on trying to get every validator client compatible with every beacon node. So that's quite a big matrix. And that should be compatible with every execution layer node. And you can see I think in Curtosis already in the page, we have a matrix of which combinations don't work. You might see some chatter about this on the interop channel as well. And we're slowly ticking them off one by one. We're getting there, but we primarily use Asserter to figure this out. It can also be run locally. So like I showed you earlier via Curtosis, it has Asserter built in, or you can integrate it into a CI. So there's an Asserter GitHub action, and you can use this GitHub action in your repository. That's what we've done with the Verkle DevNets repository. So that just calls Asserter, points it at in that example, a Kubernetes cluster. It does a shadow fork, and that shadow fork, as seen here, that shadow fork does the Verkle conversion check. The test, as you might have guessed, can also be a local definition. It doesn't have to be a remote definition. It can be a GitHub gist. It can be a notes on HackMD. It can be whatever you want it to be. So it's a very, very generalized testing tool. Please use Asserter as much as possible. It's a relatively new tool. It's only a few months old at this point, so it hasn't gotten the prime time that it deserves, but we're hoping to use it more. And for those of you who attended Mario's call, you might notice that it has a lot of overlap with Hive. So Hive also does a lot of assertions, right? It says, I give this transaction. This is the EVM state transition that needs to happen. Did that happen on this node? Hive does this. So why did we build a whole new tool to do this? Because the way Hive is architected, it's very, very nice for single nodes. It is possible in Hive to do interop multiple node testing. It's just more cumbersome. And Hive is built such that each test takes a very short-ish duration of time. You can configure it to do a longer duration. It's just not made for it. Asserter doesn't have those assumptions. A deposit, for example, on a perfect network level thing takes like what, half a day to process through the queue. Hive it's not necessarily multi-threaded in the same way, so it might, depending on how you configure it, get stuck on that one deposit until it's processed by the network before it moves on to the next test. So Asserter is just built from the ground up to work in a network-wide scenario. So the way my mental model works is Hive is what we will always use for single node, black box level testing, and Asserter is what we'll use for network level testing, where the network itself is a black box and I just want to assert behaviors in a network. So they're very synergetic. Ideally, Hive finds all the critical bugs before it gets to the Asserter level, but if it does, then it's also nice to have these two tools that can kind of compare outputs and say, hey, this should have failed in Hive, why didn't it? Or this should have failed in Asserter, why didn't it? To give us this level of flexibility that we can benefit from. So please try this out. Yeah, let us know if you have feedback, and we'll be announcing it more widely over the next weeks. Now for a bit smaller CLI level tools. Some of you might be tempted to work on the fork choice. Whichever deity you believe in support you in that endeavor. It's a difficult field, and it's very difficult to understand what is going on with fork choice. Hence, we built Forky. So Forky is a fork choice visualizer. It relies on the beacon node standard API, so every single node supports it. And what this does is it connects to nodes that you've linked it to, and it visualizes the fork choice. You can also upload a fork choice from your local node, and it will visualize this for you. It sometimes helps with fork choice debugging to see the tree of what was built on what and what weight something had. It really, really helps in a critical situation. This can run in as a binary, as a Docker file, as a Helm chart, as Ansible, under Curtosis. As you see, we support a wide range of things. And if you're ever intrigued what the fork choice on mainnet does, please don't take the instance down by 1,000 people calling it at the same time. But let's see if the auto scaling works well. Go to this URL and you will see how the fork choice on Ethereum looks exactly at this moment. You will see tiny lines at the bottom as well. Those lines are snapshots that are being taken once every slot. So you can also share that snapshot link with someone, and it links to an S3 bucket. So even one day later, if you want to debug something, it will load from that snapshot. And yeah, it's a lot of quality of life improvements we spend some time on. The next tool I want to talk about is Tracer. It's still an active work in progress. I don't know how many of you have worked with the Trace API yet, but it's not the most standard thing in the world. And when there's a big mainnet incident, traces tend to be the first thing we go to, or one of the first things we go to see. So we have a mainnet tracer. It connects to one of each EL and CL, and what it does is every single block, it traces it, uploads it there. Every single slot, it gets the beacon SSE, the state SSE, it uploads it there. It has instructions on how to take the traces from two different ELs and then compare them to see if there's a diff. Ideally, in mainnet, there's 0 diffs. But when there's an issue, the diff helps us find out where the problem was. And with the state.sse, what you can do is you can take the previous state, the next state, and then you can use a host of tools to go through this transition. Ideally, every single one of those tools gives you the same output. If it doesn't, you have a problem and you need to figure out why. And this tool kind of is a tool that we hope to never use, but when you need to use it, it's something we want to use. We had a blog post about this recently. And in the same form as Checkpoint Z, the team has built this tool, but ideally we would like the community to run it. We don't want to run this ourselves. As an ethos, the ETH Panda Ops team tries to never run anything for mainnet because we don't want to canonicalize what mainnet is. That should be dependent on the community. We tend to just run stuff for testnets. We are running Tracer for mainnet purely until the network effects of community running these tools builds up. This really helps. So if you have a lot, then please do. The next one is Dora. So Dora is a lightweight beacon chain explorer. Extremely extendable. So we have Dora for Verkle, we have Dora for Holsky, you have Dora for everything. Even the beacon chain guys run Dora as a backup in case beacon chain has a problem. It gives you low-level access to the database, so much so that you can run Dora, and very often when we want to do some MEV style analysis, we just run like a SQL query against the Dora database and we get the information that we want to do. It's very extendable, very useful. Please have a look. Easy to run. And Dora has a built-in like fork visualizer. So if you have 10 nodes, it'll tell you if 2 of those nodes are forked off or whatever. You can do EL forks, CL forks. Does all the nice things. The next one and last tool I'm going to talk about today is Zatu. Anyone who is really interested in data and data visualization should be paying attention to these two repositories. The Ethereum peer-to-peer layer is notoriously hard to get visibility about. There's a lot of noise to go through. There's millions of events that go through. Okay, that's something different. There's millions of events to go through. There's literally every slot, a couple million or a couple 100,000 attestations that go through, right? So what we did is Zatu analyze or collect all of this data, puts it in a shared database, and then you can use a tool like Grafana that visualizes this, but the database can also be queried directly. all the data, or almost all of the data that Zato has, is open sourced. We're still on the process of open sourcing whatever's left over. And in case you're someone who's interested in the data challenge that the Ethereum Foundation's organizing right now, please have a look at the Zato data. It might save you a lot of time from collecting your own. The way it works is we have these things called Zato sentries. So these sentries collect to a consensus node, and it uses the event stream. It fetches the event stream, it annotates the data, and pushes to a Zato server. There's another crawler that does some disk v5, disk v4 stuff. There's something else that collects mempool data. All of this gets backfilled, put in a Zato server, and this is persisted. I think we have over a year worth of mainnet data in this pipeline, couple billion rows in it. There's a lot. And all of this gets ingested into a data pipeline. And the reason it goes into a data pipeline is the questions you want to answer are not apparent from the data. You might need to do transformations. You might need to do some amount of analysis, right? And you want to canonicalize these analyses. So we have an entire data pipeline built for this already. And the output of the data pipeline can be graphs like this, where you can see a heat map of when attestations arrive at which millisecond in which network. You can see how long they took to propagate along the network. So something you might find interesting is usually there's a strong heat map at the 4-second mark, because that's when there's an attestation deadline and proposals tend to go through then. Before that. And you can also look at blob sidecars and when different nodes saw it, and you can create like a P95 metric for this to know, okay, I have 100 nodes in 50 different locations, and 95% of them saw a particular number of blobs arrive well under a certain time that we expect the network to handle in a healthy manner. This allows us to make really deep decisions on Ethereum, how many blobs to have, how the propagation statistics look like, etc. And the entire stack is reproducible on testnets. We do reproduce it on testnets, and it helps us answer a lot of these questions. One thing we're still working on is trying to automate more analyses. So you might notice in the ETHPanda Ops blog, we have one manual analysis done for the mainnet Denkun fork. We're trying to analyze and figure out how to better get that kind of output without someone having to sift through the data each time. There's some answers to use stuff like local LLM models to analyze the data. Still not really happy. If someone wants to explore that side, please do. The data is all out there. So yeah, I think that's a great synergy that could exist. And what next? Like I was mentioning, I think in most of the call, the highest value thing I would like you guys to take away is how to run your local DevNet and how to do a prototype. So please, at the bare minimum, fork a client, add hello world to the terminal output, run Curtosis with your forked client, and be happy that your name is printed out in the get logs. And that's just a gateway to get you into knowing how the system works, into how you can extend it. There was someone last year from the protocol fellowship who worked on a version of, I want to say EPBS, but I'm not particularly sure if it was EPBS or not. And he used Curtosis extensively for his testing. And once he was done with Curtosis for his testing, he also migrated the entire stack onto the Gurley network, I think. And that helped give us a lot of insight into what works, what doesn't work. He worked with the researchers to do some analysis on how difficult the implementation might be, what edge cases might exist, and so on. And I do think that everyone should use tests and testing as a great starting point, because it's a really nice way to learn how Ethereum works. Please, again, go through whatever Mario has shown you guys in the last talks. The testing team is amazing. They're very accommodating, and we are really accommodating as well. So if you feel like you want to contribute to any layer of the testing stack, please do. Write tests, write Asserter tests, write Hive tests, write spec tests, whatever they are, and that gives you a new understanding of how Ethereum works, what the edge cases are, so that when you're working on whatever you want to work on, you know what the entire space looks like and what considerations you might want to have. And thank you. Help us with testing the next fork. Follow GitHub, follow me on Twitter, and we hopefully still have some time for questions.
Awesome. Thank you very much, Perry. That was great. And it was a lot. That's why I was saying in the beginning that you became kind of a powerhouse of these tools because there are just so many of them. And I just want to repeat what you said. Like, it's one of the great ways to learn how Ethereum works, and just running all these tools, like connecting them to your client and seeing the metrics, seeing what is actually happening there. It's really great. And also, so what you said, that you can avoid running it on the mainnet publicly. So, guys, if anybody wants to host this, feel free, I guess.
Yeah.
I was actually running Tracer on my node. I was trying to figure something out. I didn't, but I read it, and maybe I should have hosted. That's pretty cool to know. Yeah, thank you, Pari, for everything. It's been quite a lot. So people, like, the dominant question is that people want to see you do some demo, some practical experiment. But I'm not sure whether we have time for that, and whether you're available. And you already mentioned many things that people can try themselves.
I can, if you want, quickly run a Curtosis test on something and show you guys how that looks. If maybe that's the easiest first thing to do. But if there's any other questions, then maybe we can do the questions before that.
Yeah. Right. Yeah. People wish for the practical experiment. Another question
Okay,
coming
sure.
in. Okay. Yeah, people are asking about the Python specs, or like the spec tests, like whether you use them at some point here, and yeah.
For Python spec tests, so that tends to be more of individual. So the way we kind of have defined or divided the territory so that we can both specialize a bit more easily is anything that you can expect to be tested on a single node. Mario testing team, Python spec team, they handle it. Anything that is expected to be tested at the interop level, the ETH Panda ops team tests. So that's ideally how we've defined them. So I personally rarely run spec tests. I help maintain some of the servers that run spec tests, but otherwise I don't run the spec tests myself.
Right. Yeah, makes sense. I guess it's also like the progress where it comes from, like specs and implementation. The client teams need to test themselves, and then it moves to the interrupt. So like you're already the other side there. Yeah. Just for the context, because people are also asking about the Marius topic, I would just point you to the week 4 there. That it's all nicely explained there. Cool.
Okay, if someone wants to maybe see a small example, I can show a real world use case of a problem we had last week and we are still sort of facing, but we wanted to see. So when you run this, or when you ran this last week, what would happen is the first version, the first participant, was just a CL Teku, the default EL is geth, works fine. Teku builds in the validator. So the validator and beacon is in the same process. This proposes blocks, 0 problems. The next one is separate VC. So in this one, you have a Teku beacon and a Teku validator client. And this works fine as well. It proposes blocks, it can attest, everything is okay. But when I do separate VC and snooper enabled, then it was failing. And we didn't know why. And the reason it was failing is that the Teku beacon and validator client use a binary octet stream to communicate whatever the payloads that they want to communicate. And we have, I might have to share a different screen. So we have, one second, let me just share my entire screen. Yeah. So yeah, you guys should be able to see this. So we have this one tool that was built by each streamer called JSON RPC Snoop. So JSON RPC Snoop is built in Rust, and this tool was not able to understand a binary octet stream because when that was hit, it was hitting edge case. So you can see it tries to unwrap it, and that didn't work out. And then it errored out and it crashed. And sorry. So, and it crashed, and we weren't able to figure out what was going on. So the practical way we figured out what happened was then we spoke to the Teku team to ask why this was potentially going on. And then we had the aha moment. Oh, yeah, it's probably because of octet binary stream. You can disable that. So what we did is we added this extra VC parameter. And this says, don't do that. Just give me SSE. I'm happy. And with this, I was proposing again. So I knew that it was because my JSON RPC snooper was broken. So now the only variable that was left to do is remove this, update the JSON RPC snooper, and then I have to update the image, right? So what I did was in my local version, I would do one sec. Yeah, in my local Docker image, I was updating this. So whatever paritosh.json rpc test 1. And then I can run this exact same test. Oh, 1 second, sorry. Like this. And now what happens is this exact test definition that I know is broken will use this Docker image instead of what was configured in the remote repository. And I tested this extensively locally. And once it worked, I was happy with the solution. I made all the requisite PRs, and then we considered this a resolved issue. We found something else with the event stream. We're still trying to figure out that something else. So if someone wants a moderately difficult problem, try this out. Try out this config, and you will see that Teku proposes blocks, but every now and then it fails with a proposal, just the third participant. And then go to the JSON RPC snooper and figure out why it's failing, and make a PR, and we're very happy about it. And I showed you how to test the entire thing locally, so you know how to reproduce it, you know when it's not failing. Yeah, you kind of got the entire picture of how we do prototyping and fixing. None of this requires me to talk to anyone outside of myself. I can test this a million times. I've never written Rust code in my life. I was able to use different tools to understand what the error might have been and try out a few solutions myself without having to push any big changes without knowing it works. So that's a practical example. Yeah, I mean, I can just run this for you if you want. It'll take a while, but you can see all the steps it goes through. Oh, well, yeah. And as you can imagine, this fails immediately because this image does not exist. So let's switch back to normal. And this will most likely work. It will spin up all of my instances. It'll create Genesis. I know we're already out of time, Mario. Is it still okay if I take a few minutes to finish this?
Of course, it's only up to you. We don't want to, take your time. So if you're free, it's okay, right? People are still listening, and very thankful for the experiment. Very excited. It's great to see it run, and it's a great example, by the way. I mean, current issue and relevant. Also, because last week we had in this call we had Paul from Teku. Explaining the Teku architecture, so they should have an idea what's happening.
Perfect. Yeah. Perfect. So if someone wants to make a PR fixing all of our problems, we're very happy.
Awesome.
Yeah, it might just take a bit because it also has to download the Docker images, but hopefully does not take too long. As you can see the steps, it kind of goes through the configuration. It just deploys one by one things that need to be deployed. It will fetch peering information. It'll set up peering as expected. And I hope you also see kind of this benefit of having an overridable approach. If I add VC extra params, I know that my validator is running with one extra parameter, and I can test something that the other validators don't have. So you can do a lot of iterating testing this way. Yeah, it should just be, creating the validators now. And maybe one example of how this looks under the hood, if I do docker ps-a, see a bunch of Docker containers with tasks, and you can see my ELs here and my CLs here. But I don't recommend interacting with Curtosis that way. If you wait for this to get done, the Curtosis CLI itself allows you to get all of this information in a much nicer to see way. You can interact with it directly with Docker, nothing stops you, but it will give you all of these, for example, URLs. If I was to go to this URL, it'll open Dora for me. So I will quickly just share my screen and show you how Dora looks. So this is Dora. It's running on the DNeb fork with my local DevNet, which has 3 Geth participants. You can look at the blocks, you can look at the graffiti, you can see everything, you can see the validator key. And the error I'm talking about essentially happens with the first one, the missed block that shouldn't have been missed. And if I was to do Curtosis service logs, then I specify my enclave name, and then I specify the instance I want to get logs from. So please use autofill, it works really nicely. And then I want to follow the logs. And this is my logs from the third CL. And you can see there is some error, but that's about validator fee recipient, nothing else. Otherwise, it looks quite okay. And it just built a block on slot 12. So if I wait a second, slot 12 was built by 3. So that whole system works. And for example, if I do snooper beacon 3, this is the snooper for beacon 3, and you can see all the request responses that are coming through on that interface. And then what else is interesting? Well, yeah, just look at service logs, and if you ever need to know what's going on, inspect enclave. I forgot the enclave inspect command, but you can inspect what is running in a running enclave as well. Yeah.
Great. Yeah, thank you so much. It's really great. So you basically, like, instead of the Docker tooling, you have this Curtosis wrapper, which gives you all the options, and it's crafted for this. That works really nicely. Yeah, amazing. I think it's a few minutes over, and I didn't really want to hold you up longer, but huge thanks for going the extra mile, for giving us the demo. We really appreciate it. I personally love all the DevOps tools, and it's really fun how you just go further, and we see, oh, there is also JSON Snooper, there is also Snapshotter, there is always something we are working on in the background. So so yeah, thank you so much for all of your work, Pari, and especially for this presentation. It was a great learning experience. Yeah, people are trying the Curtosis. They are asking some questions in the Discord. If you join the Discord, you can maybe interact there if you have a minute. But it's totally up to you. I will share you the link later. But to all of you folks who've been paying attention, thank you so much. I hope you learned something. And if you have some extra questions for Pari, or if you're trying these things, please share your results with us. We're very thankful that you gave like very good specific examples of what people can practice, what they can try afterwards. That's very helpful. And yeah, and I'll see you folks on Wednesday for a talk by Piper Marianne, and we can wrap it up here. Yeah, thank you very much, Pari, again. Appreciate it.
More than welcome. See you guys.
Bye bye.
Bye.